Hi, today I'm very glad to share some performance results of the TVM AutoScheduler for the Andes vector processor. This work was done by Yuanming Zhang, Hao Yan, and me, Alex Wu. All of us come from the Andes Technology Taiwan. In today's talk, I will make a short introduction to our vector processor, NX27V, TVM and AutoScheduler. And next, I will describe what we do when supposed to run AutoScheduler on Andes platform. And then I will show some experimental results. And then finally, we will make a short conclusion and list some future works. NX27V is a vector processor designed by the Andes. It consists of efficient scalar code, main-boost memory system. This memory subsystem can improve the memory performance significantly. Furthermore, and most importantly, NX27V has a very powerful vector processor unit. This vector processor unit can support different data types, including data types defined in the RISC-V vector spec, such as integer 8 and floating point 32. Moreover, it also supports bfloat 16 and integer 4. These two data types are extended by Andes. The vector length, SIMD width, and the memory bus width are configurable in the NX27V. In the NX27V, all vector instructions start to execute after retire. This means the vector instructions do not block the main pipeline during the execution. To have a better performance, most function units in the vector processor unit are pipelined and trainable. Due to the time limitation, I can give a more detailed description on NX27V. So if you have interest on this CPU code, please search the RISC-V Extension Mystery on YouTube. You can find a more detailed description on this processor codes. TVM is an open-source machine learning compiler framework. It can support several CPU and GPUs. Furthermore, it also supports most widely used machine learning frameworks such as TensorFlow and PyTorch. Currently, TVM can support two different modes to build and run machine learning models. One is JIT mode, another one is bundle mode. The main difference between these two modes is when to build and when to run the machine learning model. In the JIT mode, machine learning model is built and run dynamically, while in the bundle mode, machine learning model is built ahead of time. To load the input data, running machine learning model and get output result, TVM also provides a runtime library. However, current runtime library cannot support experimental platform. That means this runtime library must run with OS support. To overcome this problem, Andes pulled a version of runtime library by removing all functions that must depend on the OS. Therefore, we can run our machine learning model on the Andes platform without any OS support. This figure shows the architecture and the built-in flow of TVM in the bundle mode. In this model, the input of TVM is a machine learning model. The output has three. The first one is the binary of machine learning model. The second one is the field weight. The weight comes from the machine learning models. The next one is the model graph. This graph is meant to list all operators defined in the machine learning model. Based on this graph, TVM can know how to run the whole machine learning models. After generating these three files, user must write a program used to call TVM runtime library and assign input data, run the model, and get the interference result. Finally, user build their application code and link the model object and the TVM runtime library to generate the final executables. And then they can run their executable on the platform they need to run. AutoScheduler is an optimization path in the TVM used to find the optimized solution for a given machine learning models. The main step of AutoScheduler has two. The first one is to partition the given machine learning model into several subgraphs. Each subgraph consists one or two multiple operators. The second step is the most important one. For each subgraph, this step is to automatically explore many optimization strategies and then identify the best one using the machine learning algorithm. Currently, several optimization strategies are used in the AutoScheduler. Here we only list some important ones, like loop tiling, vectorization, and operator fusions. This figure shows the flow of AutoScheduler run on the Andes platform. The flow mainly consists three parts. The first part is TVM. TVM used to partition the machine learning model and apply different optimization strategies on each subgraph. Then, to run the binary of each subgraph, we add a new path in the TVM to generate a wrapper code. The wrapper code is very similar with user program, like addressed in the previous slides, used to feed input data to the subgraph and then run the subgraph. The second one is the builder and is used to build a wrapper code and link a subgraph object and the TVM runtime library to generate an executable. The final one is the runner. Runner is used to upload executable to a board or a simulator and get the execution cycle and then feedback to the TVM for generate the next optimized version of subgraph. Like addressed in the previous page, this page summarizes all the extra work we do to run AutoScheduler on Andes platform. In the TVM, we add a path to generate the wrapper code. In the builder, we integrate the building flow with the Andes Toolchains. In the runner, we modify the object loader to run the executable on the board and the simulator, and also modify the cycle information extractor to get the execution cycle and then report this information to the TVM. Furthermore, to speed up the AutoScheduler exploration time, we also modify the runner to support multi-threading. This means the runner can run different executables built with a different optimization strategy on the multiple targets. To evaluate the performance of AutoScheduler, we apply three machine learning models. The table shown in this page lists the speed up in the three different models with different cases. In this table, the result can be classified into three categories. The first one is scalar. It means the machine learning model is built without generating any vector instruction. The second one is built machine model with the vector instruction but do not enable AutoScheduler. The final one is apply AutoScheduler and generate a vector instruction when build the machine learning models. Furthermore, in the final one, showing the last three rows in the table, there are three different strategies applied. The main difference between these three strategies is the number of iterations being applied. In general, more number of iterations being applied will have a higher speed up. However, it also implies more compilation time need to be taken. According to the paper of AutoScheduler, they claim that the 20,000 iteration can achieve a good enough result. This is why maximum number of iterations is 20,000 in these tables. Furthermore, only one string finding in this table enable AutoScheduler not always have the higher speed up. For MobileNet V1, when applied 200 of iteration, they do not have any performance improvements. Let me make a short conclusion for this talk. In this talk, we first introduced Andes vector processor NX27V, TVM and AutoScheduler. Then we explain environment preparation for the TVM AutoScheduler on the Andes platform. Finally, we give some experimental results. Since the exploration time of the AutoScheduler is very long, how to limit the search space on the spatial target to reduce the exploration time will be an interesting issue to investigate further. Another interesting issue is to apply more loop optimization on the AutoScheduler to achieve better performance. Thank you.